This is a Chip8 emulator I've written for the original Macintosh. Now, if you've never heard of a Chip8 or you're not familiar with the original Macintosh, don't worry, we'll go over that in a second, but for now, let's get this thing loaded. Now, if you are familiar with the original Macintosh, you've probably never seen a loading screen that looks quite like this. This is actually part of the punchline to the video, which we'll get to in a sec, but for now, let me get you a little closer so you can take a look at the emulator. Alright, before I explain too much, let me get a game loaded so you can get a feel for the system. So this is Astro Dodge. Now this is actually a relatively modern game made for the system. I think it was made in 2009. And the point of the game, if you can manage it, is to avoid the asteroids coming at you. Now, don't throw out your Xboxes or PlayStations just yet. The games for the system aren't gonna blow you away if you have modern sensibilities, but still, they could be quite a bit of fun. Some nice, simple fun. Anyway, what's a Chip8?
In the mid-1970s, a guy by the name of Joseph Weisbecker helped design a home computer called the Cosmac VIP. Weisbecker wanted to write games for the machine, but he found assembly programming too difficult and languages like BASIC too inefficient to run well for games. To solve the issue, he ended up coming up with an interpreted virtual machine called Chip8, which struck a good balance between ease of use and speed of execution. The Chip8 virtual machine specifies a processor with 16 8-bit registers, a 16-deep stack, and about 36 instructions. As for peripherals, it has a 16-key hexadecimal keypad for input, an extremely primitive beeper for sound, and unfortunately, only a single 64 by 32 1-bit per pixel frame buffer. This single frame buffer is why you see a lot of flickering in Chip8 games, since it cannot double buffer.
Now, if you hang around any emulator developer forums, you've probably actually heard of the Chip8 before. It's because it's a very common first system to target for any budding emulator developers. And if you are such a budding emulator developer who's written a Chip8 interpreter, you've definitely seen this program before. It's pretty simple, it just draws the IBM logo to the screen, but it's a pretty common first program for people to run because it only uses a couple of the processor opcodes. Alright, let's run something a little bit more exciting. For those of you into the demo scene, there is a Chip8 demo called Trip8. This one's actually kind of cool. It does a little bit of 3D here, as we're going to see in a moment. There you go, you got a rotating cube. It's actually pretty impressive when you consider that Chip8 doesn't have a multiply instruction. So, you know, if you want to do your 3D transformations with a matrix multiplication, that's not so easy to do. Alright, let's try something a little bit more interactive. Here we have Outlaw. This is actually a port of an Atari 2600 game. This is also our first introduction to the Chip8 sound capabilities. Now, the Chip8 has a very, very simple sound system, as I mentioned before. All it does is it lets you make a little beep. This is hard to play while you're talking at the same time. Yeah, got him. Alright, let's try another game. This is called Space Jam. The point is you avoid the little things coming at you. Presumably those are stars or asteroids or, I don't know, something space related, I'm sure. It's a little harder than it looks. You might have noticed that game ran a little bit slower than you might expect. This is a quirk of a lot of Chip8 interpreters. They'll all run at slightly different speeds, so with the plus and minus keys you can adjust the speed. So let's go up a little bit, and let's try that again. You can see that's running quite a bit smoother now. Yeah, I'm still not any better at it though. There was later a slight extension to the Chip8 made called Chip8 High Res Mode. This doubles the vertical resolution, going from 32 pixels tall to 64 pixels tall. I don't actually see a lot of interpreters implement this. Not quite sure why. It's pretty easy to do. You just have to do a quick check and then make the frame buffer a little bigger, but I've implemented that, and Trip8 is available for this high-res mode. There you go. You might notice that it's actually taking up the entirety of the Macintosh display now instead of just being windowed a little bit. I did actually have to compress it though. I was trying to scale each Chip8 pixel 8 times to a Macintosh pixel. Unfortunately, I wasn't quite able to do that. 64 times 8 would be 512, which is more than the Macintosh's vertical resolution. So I had to squeeze it a bit. I think I'm blowing it up vertically 5 times. But still, I think it looks pretty good. While this is running, I'm going to swap out this machine for a different one, and let's talk about the computer this is all running on. Alright, I'm back with an even older Macintosh. This is a Macintosh 512K. This is actually from the release year of the Macintosh, 1984. And you might notice a circuit board hanging out. That's because this Mac's taken apart. So we can take a look inside and see what's driving this thing. The insides of a Macintosh are basically this. This is the logic board. It's everything that's the computer part of the computer. Here we have a Motorola 68000 CPU running about 7.8 megahertz. For some system architecture reasons, it's actually closer to 5.1 megahertz because the video circuitry will steal memory cycles from it. There is no clear single chip responsible for the video and sound that I can point out for you. They're all implemented as these programmable array logics that are scattered about the board. But the video in the original Macintosh, you basically get 2 frame buffers of 512 by 342 pixels. Each pixel is 1 bit, and that's basically it. You don't get sprites, you don't get any background layers or tile maps or anything like that. There's no blitter. This is an Amiga. You just get 2 frame buffers and you got to be happy with it. For sound, you get 370 locations in RAM that you can put bytes in, and the video circuitry during H-blank will actually feed this out to a DAC. So you get a little bit of a FIFO there to do sampled audio, but all of the mixing and everything like that has to happen in software. One last thing I want to point out while we're here, we have 512 kilobytes of RAM, but this emulator will run on basically any RAM configuration of Mac, including the kind of pathetic 128K Mac, which was originally released. I still quite can't believe Apple thought that machine was a good idea. Alright, time to come clean. Why the hell do I have a Macintosh here that's half taken apart? What was all that nonsense when the program was first loading from disk? What's going on here? This doesn't even look like a real Macintosh application. And that's because this isn't. This is not running in macOS, or what they called at the time just system software. They renamed it to macOS later. This is actually running completely bare metal directly on the hardware. There's no operating system or anything in between this program and the machine it's running on. All right, I have another demo running here so you don't have to stare at a menu while I do the big reveal, which is that this is the first application that I've written using a new SDK that I'm developing. This SDK is a bare metal SDK that lets you write programs that execute directly on original Macintosh hardware. So that's the following models that I'm going to show on screen here. All of these machines have a very similar system architecture, which allows basically one executable to run on all of them with some minor caveats. All of the stuff you see on screen when the program's loading, this is actually a bootloader that I've written that loads the application or operating system or whatever you want into memory and then jumps to it. And when I say this runs bare metal, I mean it. If you know anything about the original Macintosh, you'll know a large portion of the original macOS was actually located in ROM on the board. I am using none of the routines from that ROM. All of the keyboard input, video, sound, everything is handled by routines that I've written myself in C and assembly, which I'll show you in a second, and they directly control the machine. In order to write these custom routines, I had to do a fair bit of reverse engineering since a lot of the stuff in the original Macintosh isn't documented, and that's why this machine is half taken apart, so I can probe various pins with this little logic analyzer here, so I can make sure the routines I'm writing are doing the right things at the hardware level. The SDK uses GCC as its compiler. It has reasonably good code gen for the 68K, so it gets the job done. For actually directly interacting with the hardware, I've written a little library here that I call libSDK, and this has all of the functions required for doing things like drawing things on screen and getting keyboard input. For the lowest level of hardware interaction, I've of course defined a header with all of the registers, and this lets me poke the hardware directly. In fact, all of the libSDK routines use this file extensively for basically every interaction it has to do in the hardware. The actual Chip8 emulator itself is written here in chip.c. It's nothing particularly earth-shattering if you've seen a Chip8 interpreter before.
For instruction decode, I use a big switch case block. This is just because I think it produces slightly better code gen. Branching is a little bit faster than doing a jump and then having to save registers if you're doing a full function call. In the end, I don't actually think this mattered that much because this isn't actually the performance bottleneck for the emulator. The main performance bottleneck was taking the pixels in the Chip8 frame buffer and then blitting it to the Macintosh frame buffer, while also expanding it 8 times. I originally implemented this naively in C, iterating over basically every single bit in the Chip8 frame buffer and then drawing the appropriate bytes in the Macintosh frame buffer. As you can imagine, looking at all of these for loops, this was very, very slow. I then, for some reason, tried rewriting this in assembly, hoping to get much better improvements, but as you can imagine, this didn't help too much. It definitely ran faster, but I'm still, at the end of the day, iterating over every single bit in the Chip8 frame buffer, which is just inherently going to be very slow. The solution, as is the solution to a lot of things on a computer, was to use a lookup table. For every single possible byte value you could see in the Chip8 frame buffer, what are the bytes that need to be copied into the Macintosh display? These bytes can be copied using 2 long word moves, which helps maximize data bus use, and it also helps reduce how many instruction opcodes are needed. And this is a real problem on the Macintosh because the video circuitry constantly steals opcode fetch cycles from the processor, which obviously isn't great. Doing this helped massively improve performance to the point that even this C implementation of the frame buffer copy ended up being fast enough for actually using the emulator. Of course, that still didn't stop me from passing up a good opportunity to write some assembly, so I ended up rewriting it in assembly as well, just to make it a little bit faster. Now, the SDK is still under development. There's a couple of rough edges that need sanding before I spit it out into the world. And because of that, I'm also not going to release the source code for this emulator, mostly because you wouldn't be able to compile it without the SDK. But when I do release the SDK, I will release all of the source code for this as one of the example programs.
If you want to give this a try, I will be releasing the disk image now, however. It is an 800K double-sided floppy disk image, so make sure you write it to an 800K disk and boot it from an 800K disk drive. It's only going to be compatible with these models, so don't try running it on an SE30 or a Classic 2 or anything like that. It won't work. I can also confirm that it does work correctly with a floppy EMU if you own one. And finally, if you don't own an old Macintosh but you still want to give this a spin, you can use an emulator, but unfortunately there is only one emulator that emulates the Macintosh accurately enough to be able to run such a bare metal program. This emulator is MAME, specifically the Mac 128 driver in MAME. Now I know MAME is a little bit annoying to set up, but I've heard good things about a front end called Ample, which is an Apple device specific front end for MAME, so that's worth a try. Don't even try running this in an emulator like MiniVMac, those complete junk. It doesn't actually emulate the Macintosh hardware, it just patches the OS and intercepts syscalls from it. There is an up-and-coming emulator called Snow, which actually seems fairly decent. It's actually able to load the program. Unfortunately, its peripheral emulation is not very good, so you can't actually use the keyboard to use it, but still, something to look forward to in the future. I would appreciate if you do all of those annoying YouTube things that I'm sure everyone else already tells you to do, like liking the video and leaving a comment and all of that sort of stuff. I'll be doing more silly things with these old Macs and with computers in general, and also with emulation development, so if you like that sort of thing, maybe consider subscribing. You'll see more of it in the future. Anyway, that's it from me. Thank you for watching, and I'll see you next time.